So let's now turn to the Mplus script for the bivariate analysis. And I'm going to refer to the model names that we use on slide 26, where we summarized the fit to the data. So the first model is what I call model 0 on slide 26, the classic cross-lag panel model without any random intercept and with the addition of time invariance for the auto regressions and the cross-lags. So this is the model used by Oort in his paper. So on the use variable list, you have both the S variables, self-esteem, and the D variables, the depression variables. For safety's sake, we allow starts 20 different starting points, although that should not be needed for such a simple model here. And then you specify the model such that you separate the auto regressions for the S variable and for the D variable, and the cross lags for each of the two variables, and holding them equal across time. So instead of having 4 separate parameters here, 2, 3, 4, 5, that's 4 parameters, that auto regression is held equal in, so 1 parameter here, 1 parameter for the depression auto regression, and then 4 cross lags for S on D and 4 for D on S are each summarized into 1 single parameter. So in that case, then we get the chi-square here. First of all, fit function values show that there's no problem finding this solution. There's no ambivalence here about what the best solution is. And we get the chi-square value of 207 with 36 degrees of freedom. So we reject that model. But that's the model that Oort reports, and he finds then that S on D, which is held invariant, is negative and significant. Same, minus 0.12 throughout. And it so happens that D on S is also minus 0.12, significant. It's not held equal, it's just an unpedagogical outcome here. You can see from the standard errors that they're different and from the z-scores. But anyway, both of them are negative, which is what the authors expected. High self-esteem lowers depression next time. High depression lowers the self-esteem the next time. And you can look at the standardized results here, SCDYX standardization, and you get, I think what he reports in his article, minus 0.08 and minus approximately 18. Even if you hold time invariance of the raw coefficients, the standardized coefficient is going to be a little bit different because of the residual variances being different across time. Now let's then turn to the next model, and RIAR1. So that's model 6. So you may want to call it RICLPM. That's the standard Hamaker et al. Model. And we then see that the specification is now in a more compact fashion because we don't have to hold any time invariance. So in addition to the random intercept factors here, we have S and D regressed on S and D. So S on S and D on D. It's a compact way of writing the auto regression. And the auto regression is for the hat variables, that is the residuals in the regression of the S and D variables on their respective random intercept. And then this line here, second line, gives the cross lags, S on D and D on S in a compact fashion. And then you have the p-width, pairwise width variables. And that gives you a list of solutions that are all the same, which indicates that you have an easily found maximum likelihood solution. So the parameter estimates are easily determined from the information in the data. And you have chi-square of 34 with 21 degrees of freedom, which is what we reported. So that's a well-fitting model. And it has 44 parameters instead of 29 for the invariant cross-lag panel model and 41 for the non-invariant. Although you need it with CLPM, you need lag 2, which has 47 parameters, not far from the, well, it's actually more than the model we're looking at. So 47, the classic cross-lag model needs lag 2 with 47 parameters, whereas this model we're looking at now has only 44 and has a better fit. So it's just the right kind of model. So what are the estimates here then? Well, if you look at them here, S on D, that's negative, but it's insignificant for the second on the first time point. Third regressed on the second, negative but insignificant. Fourth regressed on the third, negative, and there you have a significance. That's the first one, S4 on D3. And it's the only one of the S regressions that's significant. Cross-lag with S as dependent variable, only at between time point 4 and 3 do we have significance. For the D variable as a dependent variable, D on S, positive significant. That's not what we expect, but this is the result we get from a better fitting model. D on S at the next time point, insignificant, essentially 0. D4 on S3, insignificant. D5 on S4, that's the only one then that has a strong negative significant effect. So there's a different outcome, and then you may want to start thinking about why does this happen in these real data? What are the issues here that cause these unexpected directions and of influence, and only significant influence at certain time points? Maybe you have to bring in time varying covariates into this model. And what are the effects in the standardized metric? If you just look at the significant ones, minus 0.31, that's substantial. And for the D, plus 0.21, also substantial, and minus 0.30. In any case, those model results contradict those from the CLPM model, and you would tend to put more faith into the results of this analysis because it fits the data better. It's closer to the data. So finally then, if we look at model 7, the RI-ARMA model, which really is a little over-parameterized for only five time points, but we want to show what it looks like. So here you probably need starts equals 20, perhaps 50, perhaps 100. So what you do here is you revert back to the old way of specifying RI CLPM models, namely introduce a factor behind each observed variable with residual variance is 0, as in the classic way of portraying the Hamaker et al. CLPM, RI CLPM model. And here you have to set some unwanted covariances to 0 between factors. You can have model equals no cov as well. That would work fine. Then you wouldn't have to say that. And then you specify in this compact form the factor for S, regressed on the factor for S. That's the order regression of order 1. Same for the D on D. And here are the cross-lags. Sorry, not the cross-lags, but the MA, the moving average component, FS3 to 5 on FS2 to FS4, deleting the first time point, regressing on the first time point for reasons we discussed in the univariate case. And then the MA part for the D part of the model, same way. Using the hat language here, but now it's hats for factors, not for the variables. So here you have the cross-lags, S on D, D on S. And then you have the p-width statements. And that gives you the, well, let's see first. Here we have, here you actually see that you have a couple of different solutions, 12 and 17. So this is a bad solution we got. And 17 starting value runs did not even converge. So here you see that the model is difficult. The likelihood, one could say, is doesn't have a well-defined maximum, global maximum. So you may want to, but it could be quite bumpy, so hard to tease out all this information from the data for all the parameters in this model. We even want to run it with 50 starts or even 100. I think I did that and found no difference. That is the best solution at the top there. But we have some comments here on problems for the model. And we're just going to take a look at the, let's say, see if the residuals, well, we have a negative residual here. So it seems like it's not the right model. Now, what about the on statements? I don't know how much credence we would give to them, but we have insignificant S on D, insignificant S on D still, positive but insignificant, insignificant. So none of the S regressed on S regressed on D are significant. But let's see, and we have only one D regressed on S significant. So in that sense, to some extent, the RI-ARMA model and the RI-AR model agree. And there isn't uniform cross-lagged effects across time, and therefore the invariance model is not appropriate.